Now I'm going to become your BFF by looking at a function f of x equals x squared, which is not only integrable, but it's going to satisfy the mean value theorem. So if you remember, we used inscribed and circumscribed rectangles to verify that the definite integral from 0 to 3 of x squared with respect to x actually equals 9. Here's a nice visual of that, and since our curve is entirely on or above the x-axis, it actually is exactly equal to the area of this region that I shaded in between x squared and the x-axis. So what we want to do is, now that we know that f satisfies the mean value theorem because it's continuous on that closed interval 0 to 3, we want to find the c that's in that interval that satisfies the mean value theorem. So recall the mean value theorem, the definite integral from 0 to 3 of x squared with respect to x is going to equal f of c, where that c is some value in between 0 to 3 or on the endpoints, times b minus a. So what we really need to do here is say that this equals 9, so we knew that from what we did in a previous video, right? And then f of c is going to be c squared times b minus a is 3 minus 0. So this becomes a pretty easy process here. So we've got 3c squared equals 9. So c squared is going to equal 9 divided by 3, or 3, which implies that c, when you take the square root, it's plus or minus, so c equals plus or minus the square root of 3. Well, the square root of 3 is about 1.732, but the one that we want here is the positive square root of 3 here. And so really, if you remember what this is, the mean value theorem is talking about the average height of the function, mean being average, value being height value. So the average height value, and what we're really doing here is, if this is 1, 2, 3 here, the square root of 3, about 1.732, would be right here. So here's c, which equals the positive square root of 3, or about 1.732. And then what we have here is f of c, my height here, is f of the square root of 3 is the square root of 3 quantity squared, which is 3. So maybe it's not quite drawn to scale here. It might be, really need to be, if that's 9 up there, a little bit higher. But the reality is, if I take a height of f of the square root of 3, which is 3, and then I have this rectangle here, basically the definite integral from 0 to 3, which is, in this case, the area under that curve, that's going to be the exact same as the area of this rectangle, where basically we look at f of c as the average height times the width of the bottom there. So the average height times, so basically it's the base times the height here. So we can turn that in to the exact thing. So this is this change in x here is actually 3, so the width is 3, or the base is 3 there, times the height of 3. 3 times 3 is 9. That gives us the exact same value in a totally different way. So once again, we had used inscribed rectangles to verify that that definite integral was 9, so we already knew that. And then what we can do here with the mean value theorem, because f of x equals x squared is continuous on that closed interval because it's a polynomial, right? We know that this definite integral equals f of c times b minus a, and then utilize that, plug in c everywhere there's an x, and then solve for c, but make sure the positive one is the one that's the element of including 0 to including 3. So notice, I do want to mention one thing. If we actually went from -3 to 0, we'd have a mirror image through the y-axis. The area would be the exact same. It would be 9, the definite integral from -3 to 0 of x squared. But the c that we would want if we had that mirror image picture would be the negative one. So we do need to be aware of that, need to make sure that we're in that interval. But here's a very nice example that hopefully allows me to be your BFF.